Hello.
Hello.
Okay, so good
Okay, so good
afternoon.
afternoon, everyone.
So today is the
So
eighth
today is
week of
the eighth week of the
fundamental
course Fundamentals of
quantum
Nano and
photonics.
Quantum Photonics.
So this is the last
So this is the last
we will
week in which
discuss
we will
about
discuss about nanophotonics,
further
and
four
further for in the coming
weeks we will
4 weeks we will discuss about
to quantum
the quantum
photonics.
photonics.
So
So
let's start
let's
today.
start today.
So far
So far
we studied
we studied materials
and different
and different cavities
like photonic
like photonic crystals, plasmonic
that
cavities, dielectric cavities,
studied.
and we studied their properties.
So today we
So
will
today we will discuss about
how atom
how atom
reacts with
reacts with cavity
and the
and the resonant processes.
so
So
so we will
So we will, in the last class also,
talk
we were talking about
the two levels
the two level system, and we defined how the absorption,
and
spontaneous emission, and stimulated emission
occurs
occurs, and
described regarding
described regarding grazing. So
consider a two
consider a two level system
E1,
E1
E2
and E2,
and
and
one photon
one photon
will come.
will come.
It will
It
interact
will
with
interact
the
with the
of
electron
energy
of energy h nu,
and it will go to
and it will
the
go to the excited state.
so this
So
is
this is
termed as absorption
termed as
and
absorption,
three
and the three
Einstein
Einstein and the
and we
and we studied
about
about
the Einstein
the
coefficient
Einstein coefficients
A21,
A21,
B12
B12,
and B21
and B21 corresponding to absorption,
spontaneous
spontaneous emission,
and B21
and B21 is the stimulated.
so
So
atom
atom.
what is
So
absorption
what is absorption? If the atom is in the ground state,
then
then
it will
it
absorb
will absorb a photon and
the
will jump to
excited
the excited state.
then
Then
spontaneous
spontaneous emission,
then
then
spontaneous
spontaneous emission,
then spontaneous
then spontaneous
is
emission is
the excited
when the excited atom
will emit
will
photon.
emit photon randomly return to the ground
This
state.
was
So this was the
so this was
so
the
this was the
so
so
the
the
if the transition
if the transition of electron
excited
from
state
excited
to the ground
state to the ground state,
then it is
then it is the
spontaneous emission.
spontaneous emission.
And when
And when
the photon
the photon
when the electron
when the
is
electron is
excited
excited,
electron
electron
comes from the
comes
excited
from the
state to
excited
the
state to the
ground state
ground
and the
state,
photon
and a
triggers to
photon
emit
triggers to
second
emit a
photon
second
which has the
photon which
same
has the
phase
same phase and the
then it is
frequency, then
considered
it is
as a
considered
stimulus.
as a stimulated emission.
So
So
now
now
when will the
when will the
maximum
maximum
resonance
resonance
or maximum
or maximum
absorption will occur?
absorption will occur?
So
So
maximum
maximum
absorption
absorption
So the
So
maximum
the
absorption
maximum
will occur
absorption
when
will occur
photon
when photon
energy,
energy,
that is h
that is
nu,
h
will be
nu, will
equal
be
to the
equal to the
difference
difference
match level
match
spacing.
level
That is
spacing, that is
h nu is
h
equals
nu is
to
equals to
E2 minus
E2
E.
minus E1.
Then only
Then
the
only
maximum
the
absorption
maximum
will occur
absorption will occur,
because
because
now it is at
now
the
it is
resonance
at the resonance condition,
where
where
frequency is
frequency is
omega naught
omega naught
upon
upon
2 pi. That is
2 pi,
omega
that is
equals to
omega
2 pi.
equals to 2 pi nu.
And away
And
from
away
resonance,
from
we saw
resonance,
in the
we saw
previous
in the
lecture
previous lectures also, when we were discussing these things, that
when will
when will
when the material
when
will
the
be
material will be
in the
transparent, or
material.
when the material will be
So
reflective.
at that
So
point
at
also
that
we
point
talked
also we
about the
talked
maximum
about the maximum
will
resonance
occur
will
at the
occur at the
for the energy
for the
difference
energy difference
matches the photon
matches the photon
frequency.
frequency.
When photon
When
energy
photon energy
equal to
will be
the
equal to the energy
level
matches
spacing
level
and
spacing,
away
and
from the
away
resonance,
from the
that is
resonance, that is
detuned
detuned
frequencies, the
frequencies,
absorption
the
will
absorption will,
suppose
suppose
suppose we will
suppose
have the
we will have the
resonance
resonance
at this
at this
wavelength,
wavelength,
then the
then
maximum
the
absorption
maximum
will occur
absorption will occur here,
and the other
and the other
frequency
frequencies
is zero.
is zero.
Absorption.
Absorption.
So here
So here
at these
at these
these
2 points, these are the detuned frequencies.
so
So
absorption decrease.
absorption decreases.
Then what about
Then what about line width?
so line width
So
will
line
decide
width
the
will decide the FWHM.
so if there
So if there is,
if we are at
if
the
we are at the sitting
sharp
at the sharp
resonance
resonance
frequency
frequencies, and here
with less
with
FW.
less FWHM,
So we saw
so
that
we saw that it is
the
the
FWHM is
FWHM
very
is
narrow in
very narrow
gases,
in
that is
gases, that is in the
sub-nanometer,
sub-nanometer,
and broader in
and
the
broader
solid.
in the
For
solids.
example,
For
gallium
example,
arsenide
gallium
30 to
arsenide
40
30 to
nanometer,
40 nanometer,
and for the
and for
quantum
the
dots it
quantum
is
dots it
20 to
is 20
25.
to 25 nanometer.
Means
Means
if you have
if you have,
so assume
assume
you have
you have
quantum dot
quantum dot having
cadmium
cadmium
selenide
selenide
ZnS
and
core shell
ZnS core cell,
PTSC
PTSC resistance
core shell,
core shell,
and
and
it
it
its
its
emission
emission
wavelength is
wavelength is
620 nanometer.
620 nanometer.
So
So,
but still there is
but
a
still there is
some
a
range.
some
So
range.
suppose
So
if it is
suppose if it is
very sharp,
very sharp,
then there will not
then
be
there will
broader
not be
spectrum.
broader
So
spectra. Okay, so
it's
it's
620.
620 nanometer.
But
But
in real
in
case,
real
it
case,
is
it
like
is
this
like this: 6
10,
10
620,
620
630.
630.
So it will be
So it will be like this.
so.
So in this reason,
So this is the
so this is the
emission.
emission wavelength range.
So for the
So
quantum
for the
dots
quantum
also,
dots also, the
the
diffraction monopolies are depending on the.
there are several
There are
quantum
several
dots
quantum, very nice quantum
also
dots
which has
also, which has a
sharp
very
wavelength
sharp wavelength,
of
that is of order of
uh,
uh,
5
like
nanometer
5 nanometer
within the
within
emission
the
wavelength,
emission wavelength, with
having the 5
having the 5
nanometer range. Okay.
nanometer range. Okay.
So next
So
is
next is
the
the
classical
classical
versus
versus
quantum view of
quantum view of
population. So we
population.
talk
So
about
if we talk about
classical.
classical, we consider,
Suppose
suppose
we have the
we have the and
have
we have
levels
two levels,
N1
N1
and N2.
and N2.
Statistical.
Statistical.
So
So
that
that
number of
is number
atoms
of atoms in the ground state and the excited
we are
state. So if we are
considering
considering a
classical case,
classical case,
that is we
that
consider
is
the
we consider the
statistical
statistical
probability or
probability or
statistical mixture
statistical
of
mixture
number of
of
atoms.
number of atoms.
So
So
in terms of
in terms of
the
the
statistics,
statistics,
classical life
classicalized
statistical mixture,
statistical
we deal
mixture,
with the
we deal with the
probability.
probability.
So
So
and we are
and we are
considering
considering
in this case
in this case
there is
there is
no phase
no
relation
phase relation
between atoms.
between atoms.
So the
So the
probability
probability is
by
defined by
C1 square
C1 square
and
N1 by N naught
and C2
and
square
C2
and 2.
square is N2 by N naught.
In this
In
class,
this classical case,
there is no
there is no
coherence. That
coherence.
is,
That
the
is,
atoms are
the atoms
independent
are
of each
independent
other
of
and
each
there
other
is no
and
phase
there is no
relation.
phase relation.
But in case of
But in case
quantum,
of quantum,
there is a
there is a
coherence. So
coherent
we can
superposition.
write
So
the
we can write the wave
probability
function
psi
as psi is equals to C1
first state
first state
and
and
C2 second
C2
state.
second state.
If there
So if there exists a relative phase between
one and
one and first
first
state
state
and second state
and it is
and
fixed,
it is fixed,
then
then
these are
these are coherence.
and it will lead
And it
to
will
an
lead to an
interference effects
interference
at
effects
quantum
at quantum
level
level
that we can
that we
consider
can
as
consider the
double
analogy
slit.
is double slit.
And analogy
An
is double
analogy is double slit
interference.
interference.
So then
So then,
when
so when
the atom
the
will
atom
interact
will
with the
interact
cavity,
with the
it can
cavity, it
interact
can interact
strongly, it can
strongly, it can
interact weakly.
interact weakly.
So then
So then
there is a
there is a
terminology comes
terminology
Rabi
comes
oscillation.
Rabi
So what is
oscillation. So
this?
what is this?
So
So
we are
we are
considering that
considering
we are
that
applying
we
a
are
resonant
applying a
light
resonant
field
light field
to a two-level
to a
system.
two
We
level
have a
system. We
two-level
have a two
system.
level system and
The light is
the
at
light
the
is at
resonant
the resonant
frequency of
frequency
this
of this
two-level
two
system.
level system.
So
So
the
the
probability of
probability of
being
being
in first
in
state or
first
second
state or
state or
second state or
oscillate
oscillate
sinusoidally
sinusoidally
with time,
with time,
these are called
these are called the
Rabi oscillation.
Rabi
And the
oscillation,
Rabi
and the Rabi
frequency
frequency
is given
is
represented
given
by
represented
omega
by
r
omega r
and it is given
and it is
by
given
mu
by
into
mu 1 to
epsilon naught
epsilon naught by
by h cross,
h cross,
where mu one
where mu 1 to
is
this
is
is
transition dipole.
transition dipole moment,
Which is this
which is
E
this
cross
E cross A naught,
charge
that is charge cross atomic size.
E naught is
E naught is electric field,
amplitude.
amplitude, and h cross is h is equals to h by 2 pi Planck constant.
Then
Then
competing effects,
competing effects,
that is life
that is
versus
lifetime
Rabi.
versus Rabi oscillation.
So
So
excited state
excited state
has a finite
has a
life
finite lifetime,
and
and
this can be of
this
order
can be
of
of order of the
the nanoseconds,
nanoseconds,
picoseconds.
picoseconds.
Why
Why
state
state has
why the excited
why the
state
excited state has a finite lifetime?
we
Because
studied
so we
about
studied about the
emission.
spontaneous emission.
So if the
So
electron
if the electron is moving
from
from
first ground
first
state to
ground state
excited
to
state,
excited
then
state, then it can
the excite
be
also
excite also emitting a photon.
that is a
that is a
spontaneous emission,
spontaneous emission, and it can
stay for a
stay for a
small time only.
small time only.
And if
And if
the omega
the
r,
omega r, that is
the if
the
omega r
if
that
omega r, that is Rabi
is
frequency, is
too small,
too
that
small, that
oscillations
is
are very
oscillations are
slow.
very slow.
So
So
excited state
excited state
will decay
will decay
before the
before
oscillations
the
are visible.
oscillations are visible.
Because if the
Because
frequency, if the
if
oscillations
the
are very
oscillations are
slow,
very slow,
then
then
the particle
the
will
particle
decay
will decay
first, and then
first,
we will
and then
not
we will not be
able to see
able to see
Rabi oscillation.
Rabi oscillation.
So what are the
So, what are
necessary
the necessary
conditions to observe
conditions to
these Rabi
observe these Rabi
oscillations?
oscillations?
So for
So,
that,
for that,
the
the
frequency,
frequency,
the
the
frequency
frequency
of Rabi
of
oscillation
Rabi oscillations
is
should be
greater than
greater than
gamma. What
gamma.
is gamma?
What
That
is
is
gamma?
damping.
That is
And
damping rate, and
damping
this damping rate
can be,
can be,
because it depends
because
on
it
two
depends on
factors.
two
That is
factors, that
spontaneous
is
emission
spontaneous
plus
emission
diffusion.
plus diffusion.
So there
So
are two
there are
mechanisms,
two damping
mechanisms. First
mechanisms.
is
First is
spontaneous emission,
spontaneous
that is
emission, that is
population decay.
population
So
decay. So
if the
if
lifetime
the
is
lifetime
less,
is very less,
then
then
oscillation
and oscillations are too slow,
like if omega
like if
is
omega
less
r
than
is
gamma,
lesser than
not
gamma, then we will not be
observe
able to observe
the Rabi
the
oscillation.
Rabi oscillation. The
If
second is
there
if
is a loss
there
of
is a
phase
loss of
coherence
phase coherence
because of
because
collision
of
or there are
collisions, or there
phonons.
are phonons.
This is
So
this process is
this
called
process is
dephasing.
called dephasing.
Because of that
Because
also,
of that also, we will not be able to observe.
so based on
So
that,
based on
what
that,
are
what are the
the effect of
effect of
gamma or omega
gamma or omega r on the
oscillation?
oscillation?
So first
So
case is
first case is
if the
if
damping
the damping is negligible.
if the
If
damping
the
is
damping is negligible,
then suppose you
then
have
suppose you have the oscillations like this.
so over the
So
time
over the time,
there is no
since there is
damping,
no damping,
the
the
oscillations
oscillations
will not decay
will
with
not
time
decay with
and it
time,
will be
and it will be
sinusoidal for all.
sinusoidal for all the
These
time.
are
So these are called
perfect Rabi
perfect
oscillations.
Rabi oscillations.
If damping is
If damping is moderate,
that is
that
gamma
is
is order,
gamma is order of
gamma
the
is
gamma
equals to
is
zero point 0.1
equals to zero point
omega,
0.1 omega, and
oscillations
oscillations
will be visible
will
but
be
damped,
visible but damped.
right?
Right?
So you will see
So
the
you will see
oscillation
the
first
oscillation first,
and then it will,
and then it will decay.
and the third,
And the third
the
case,
damping
if
is
the
very
damping is
strong,
very
that is
strong,
gamma is
that is
equivalent
gamma
to
is
omega,
equivalent to omega r,
the
the
oscillations will
oscillations
vanish,
will vanish, and the
population
population
will reach
will reach the
equilibrium,
equilibrium,
and
and you will not be able to see the
you will not be able
you
to
will
see
not be able to see
oscillation.
any oscillations, and
Just a
it is
straight
just a straight line,
oscillation.
no oscillation, no Rabi oscillations.
So these are the three
So these are
cases
the three cases
we have to,
we have to,
for
for
observing
observing
Rabi oscillation.
Rabi
There
oscillation,
must be
there must be
the damping
the
factor
damping factor
must
must be lesser than the
be lesser of
frequency
Rabi
of the
oscillation.
Rabi oscillation.
Then how can you
Now, how
understand
can we understand
this?
this
The
the
resonators.
resonators? So
We can
we can
compare our
compare our
resonators.
resonators like this.
So
So
we are
we are
comparing
comparing here
the
with the
LC circuit.
LC circuit.
So if
So
we
if
compare
we compare with the
LC circuit with
LC circuit, then
energy,
energy will oscillate.
so
So
inductance here,
inductance here,
this gap,
this gap,
this gap will
this gap
define the
will define the
capacitance,
capacitance,
and
and
also this
also this
Because of this
Because of
material,
this
there will
material,
be
there will be
inductance.
inductance.
So
So
energy will
energy
oscillate
will
between
oscillate
inductor
between
and
inductor
capacitor,
and capacitor,
and with
and with
so there is
there is
there
there
there is some
there is some
resistance that is
resistance that is
associated
associated
with the resonator.
with the
Just like
resonator,
if we
just
have
like if
gold,
we have gold,
it has
it has
some. If
some.
we have
If we
gold,
have gold, then
obviously
obviously
has a
it has
complex
a complex refractive index. There will
loss
be
of
some
energy.
loss of energy,
So
so
oscillations will be
oscillations will
damped.
be damped.
So with
So with
resistance,
resistance,
it
if
has
it has,
what is
what is
resistance? It
resistance
has
meaning? It has some
gamma. There's
gamma.
some
There's
loss.
some loss.
And if
And
we
if
have
we
gamma in
have
our
gamma in
system,
our system, then
oscillations will be
oscillations
damped.
will be damped.
Similarly, in
Similarly,
atom
in
field
atom
system,
field system,
energies will
energies
oscillate
will
between
oscillate
atom
between
and light
atom
field,
and light field,
but
but
damping
damping
reduces
reduces
amplitude over the
amplitude
time
over the
because
time
of loss
because
of
of loss
photons,
of
because of
photons, because of
spontaneous emission,
spontaneous emission,
and
and
dephasing.
dephasing, that is,
They don't have the
they
same.
don't have the same phase.
So now,
So
how to
now how
observe
to observe
the
the
Rabi oscillation?
Rabi oscillation? So
If we
if
increase
we
the
increase
laser
the
field
laser
strength,
field
that is
strength,
the
that is
so
the,
what we
so
have
what we have
formula
the
omega
formula
r
omega r
mu 1 to
mu1
e
to
naught
e naught
by gamma.
by gamma.
So
So
sorry, so this
sorry, so
formula
this
is omega
formula is omega r is equals to
mu 1 to
mu1 to e naught by h
so
cross.
if we
So
increase
if we
the
increase the
e naught, that
e
is the
naught, that is the electric field
amplitude,
amplitude,
then we can
then we can
observe Rabi
observe Rabi
oscillation. So for
oscillation.
that, we
So
can
for that, we
increase the
can
laser
increase the
field.
laser field
So
strength.
because
So
larger
because
E naught,
larger E naught,
larger omega.
larger omega r,
Faster oscillation
faster oscillation
will be
will
visible
be visible
or damping
before damping
destroys the
destroys the
coherence.
coherence.
Next is
Next is,
so
so
how can we
how can we
observe these
observe these
oscillations
oscillations
experimentally?
experimentally?
So some
So some
experiments are
experiments are
performed
performed
on the
on
rubidium
the
atoms
rubidium atoms,
exhibit
which
the exhibit
exhibit
fluorescence.
fluorescence,
So we
and
can
so
see that
we
if
can
there
see
is a
that if there
strong
is a
coupling
strong coupling
of modes,
of modes,
then there is a
then there is avoided crossing.
how it will
How
look
it
like.
will be look like?
So these are not
These are not
these two modes.
these two modes. Suppose this is mode 1,
This is mode
this
2.
is mode 2.
So then
So then
these mode 1
these
and mode
mode 1 and
2
mode 2 will not
cross each other.
cross each other.
Okay.
Okay.
So in
So in
practice, like
practice, like
we
we
can't
can't
generate
generate
very high
very
electric
high
field with the
electric field with the
continuous wave.
continuous wave
So we
lasers.
use
So we
pulse
use
lasers.
pulse lasers.
So in that
So in that,
pulse
in
lasers,
pulse lasers,
field
electric
exists
field
only
exists only
during a short
during a
pulse,
short pulse,
and
and
so
so
envelope of the
envelope of
pulse
the
matters,
pulse
not the
matters,
carrier
not the
oscillation.
carrier
So
oscillation.
how can we
So how
define
can
the
we
pulse
define the
area
pulse area
definition? That is
definition? That is
theta is equal
theta
to
is
mu
equals
1
to
2
mu
by
1 2
h
by
cross
h cross
et dt.
et
So where
dt.
mu
So
1
where
2 is
mu
the
1 2 is the
transition dipole
transition
moment,
dipole
et
moment,
is the
et is
pulse
the pulse
envelope.
envelope.
So and
So
it's a
and it's a
dimensionless quantity,
dimensionless quantity,
and it will
and it
determine
will
how
determine how
population transfer
population
happens
transfer
between
happen between
grounds
grounds
ground
and
state and
ground state
excited
and
state.
excited state.
So next
So
is
next is
pi pulse
pi
and
pulse
pi
and two
pulse.
pi pulse.
So
So
pi pulse will
pi
take
pulse will
all
take
the
all
atoms
the atoms
from
from
ground state to the
ground state to
excited
the
state,
excited state,
and
and
during
during
spontaneous emission
spontaneous
there will be a
emission there
strong
will be a strong
fluorescence.
fluorescence.
In case of
In case of 2 pi
excited atoms,
excited atoms,
to excited
to
state and
excited
then
state
back
and
to
then
ground
back
state
to
within the
ground state
same
within the
pulse.
same pulse.
So it will give
So
the
it will give
weak
the weak
fluorescence.
fluorescence.
So
So
fluorescence
fluorescence
intensity
intensity
oscillates
will
as a
oscillate
function of
as a
pulse
function of
area.
pulse area.
And for case
And
of
for
pi
case of pi 3 pi
3.5,
5
it will
5,
be
it
strong
will be strong
fluorescence, strong
fluorescence, strong
spontaneous emission.
spontaneous emission.
But for
But
2 pi
for
4
2
pi,
pi
even
4 pi, even
integer multiple
integer
of pi,
multiple of pi,
it is
it
weak.
is weak.
So
So
this is the time
this is the
dominant
time domain
and
interference and
on the
all the
population.
population oscillations.
So we saw
So
this
we saw
condition.
this condition.
So what is the
So what
condition
is the
for
condition for observing the
Rabi
Rabi
oscillation?
oscillation? So
Condition
this condition must satisfy
R
omega r
must be greater
must
than
be
gamma,
greater than gamma,
R is
where
equals to
omega r is equals to
mu
mu
naught by
and T
H
naught by
cross.
h cross.
Gamma is the
Gamma
damping
is
rate,
the damping rate,
which can be due
which
to
can
the
be due to the
decay plus
decay
decay.
plus decay.
So in
So
gases,
in gases,
gamma is of the order
gamma
of
is of the order of 10 raised to
7
power 7
to 10 raised to
to
power
10
8,
raised to power 8,
and
and
oscillations are
oscillations
observable.
are
In
observable.
solids,
In
gamma
solids,
is of the
gamma is of
10
the
raised
order
to
of
power
10 raised
12.
to power 12.
Oscillations are
Oscillations
strongly
are
damped.
strongly damped.
So the
So
in
the in
solids,
the solids,
we are not
we are
able to
not able
the
to observe the Rabi oscillations
damping is
because
very
damping is very high as compared to omega r. So these
and
are
practically these
practically these are invisible.
oscillations
Rabi
are
oscillations
invisible
are
in case of
invisible in
solids.
case of solids.
Therefore,
So therefore,
Rabi oscillation
Rabi
is
oscillation
studied
usually
at
studied in
vapors
atomic vapors
like
like
sodium vapors
sodium vapors
or rubidium
or
and
rubidium,
also at
and
low.
also at low temperature.
So
So
observation of
observation of
Rabi oscillations
Rabi
require
oscillations
higher
require higher laser
narrow
intensity,
line,
narrow line width,
which will imply
which
that
will
low
imply that the
damping,
low damping,
and
and
these are
these are
performed in
performed
atomic
in
vapors at
atomic vapors
low
at
temperature,
low
that is
temperature, that is
cryogenic
cryogenic
conditions.
conditions.
And
And
in case of
in
solids,
case of
fast
solids,
dephasing
fast dephasing
prevents the
prevents the clean
dephasing
oscillation.
means there
Dephasing means
must be
there must be
collisions or
collisions or
phonos.
phonons.
Now,
Now,
so after
so after atom cavity interaction, there
which type of
which
cavity
type of cavity, that it can be Fabry-Paro, or
talk
we will
about
talk about more
Purcell effect.
Purcell effect.
So
So
in
in
case
the in case of photonics,
we have
we
designed
have designed
a lot of
a lot of cavities like plasmonic,
nanospheres,
nanospheres, dielectric cavities, photonic crystals,
nanoantennas.
nano antennas.
These
So these
all can be thought
all
of
can be
as
thought of at a
a
resonant cavity with
quality factor.
quality factor Q.
But now
But now
question is
the
how
question
will
is,
the two
how will a two
atom
level atom
interact with such
interact with
cavity?
such cavity?
So in case
So in case of
lasing,
lasing, in case of
making lasers,
making lasers, we are
considering two
considering
mirrors.
two mirrors.
Like
Like
we are considering
we are considering
cavity,
Fabry-Paro cavity, in
we
which
had
we had
two mirrors.
two mirrors.
One has
One has
99%,
99% reflectivity,
having 99%
having 99%
reflectivity and
reflectivity,
transmission
and transmission is order of
0.01%.
0.01%.
So,
So,
and if the
and if
constructive
the constructive
at
interference
it happen at
it happen
resonance,
at
the
resonance, so the
transmission
transmission
can
can
be
be
100%. So
100%.
condition
So
for
condition
constructive
for constructive
is
interference, suppose we have two mirrors.
particle come
Particle
back.
come back.
So
So
if there is
if there is L
constructive
constructive
interference,
interference,
L
is
or D,
L or D.
here they are
Here
considered.
they are considering D.
So what is the
So what is the
condition
condition
for the
for
constructive
the constructive
interference?
interference?
2
2
kd
kd
is equals to 2,
is equals to 2m pi,
where m
where m belongs to an integer.
and k
And k is a
a vector that
wave
is a
vector that
function
is
of
a function of
wavelength 2 pi by
wavelength 2 pi
lambda,
by lambda,
and your d
and
is
your
cavity.
d is cavity length.
Okay.
Okay.
So
So
internally,
internally,
what are photons
what are
doing?
photons doing? It will
The
build up the
intensity
intensity
by doing the
by
multiple
doing the
inside the
multiple trips inside the
ferrocavity, and the
ferrocavity,
transmission
and the
peak will
transmission peak
correspond
will
to the
correspond to the strong
intragravity field.
intracavity field.
And
And
photon lifetime
photon lifetime
in cavity is
in
equal
cavity is equals to
is finite,
is
not
finite, not
instantaneous transmission.
instantaneous transmission.
So there
So
are some
there are
factors
some
that
factors
define
that
the
define
quality
the
of the
quality
cavity.
of the
That is
cavity, that is
line width,
line width,
lifetime,
lifetime,
quality
and
factor.
quality factor.
So each
So
cavity
each
has a
cavity
finite
has a
line
finite
width because
line width because
each cavity has
each
some
cavity has
losses.
some losses.
There is no
There is no
Dirac delta
Dirac
function.
delta
It has
function.
some
It has some
losses. It has
losses.
some
It has some
FWHM,
FWHM,
and then
and then
it will have
it will
some
have some
line width.
line width.
So
So,
and in
and in
it is related to
it is
photon
related to
decay rate,
photon
that
decay
is
rate,
delta
that is delta
omega is
omega
equals
is
to,
equals to kappa,
which is cavity
which is
decay.
cavity decay rate.
So photon
So photon
lifetime
lifetime
will be
will be
photon lifetime
photon lifetime
it
in
is equal to
cavity is
1
equals to
kappa.
1 by kappa.
How can we define
How
the
can we
quality
define the
factor?
quality
Quality
factor? So quality factor
is
is
omega by
omega by
omega
delta omega, and delta
is
omega is
kappa.
kappa.
So that is a
So
decay
that is
rate.
the
So
decay rate. So
if
if
if there will
if there will
if the mirrors
if
are
the mirrors are
highly
highly
reflective,
reflective,
photon will stay
photon will stay
for the longer
for the
time.
longer time.
Photon will
If
stay for
photon
the
will
longer
stay for
time.
the longer time, that will give us the high
And
quality factor.
high quality
High
factor will
quality factor will give us the
less
less
FWH
FWHM, means
narrow line width,
narrow line width,
and it is
and
very
it is
critical
very critical for the
enhancing the light
enhancing the
matter
light matter
interaction.
interaction.
Next is
Next is
atom cavity.
atom cavity
So if we
coupling.
are
So if we
placing
are placing
a two level
a two-level atom
cavity,
inside a
the
cavity,
three
there are three
parameters that
parameters that
decides
decides
weak coupling,
weak coupling
strong
or
coupling.
strong
First
coupling.
is
So
kappa,
first is kappa, that is cavity decay rate,
that is photon
that is
decay,
photon decay,
and gamma is
and gamma is
damping factor,
damping
that
factor,
because of
that
atoms
because of atoms
non-radiative,
non-radiative decay rate,
and G naught,
and
that
G
is
naught, that
atom
is
cavity.
atom cavity coupling constant.
Then
Then
weak coupling will
weak coupling will be defined by
when so
when, so suppose we have two resonators,
and they
and they are
coupled through.
coupled through.
So if
So if
this coupling
this coupling
is lesser than
is lesser than the
cavity
cavity
decay
decay
or
rate or
atoms
atoms non-radiative decay rate,
non, it will
then
lead to
it will
the
lead to the weak coupling.
that is
That is,
the
the
emitted photon
emitted photon will escape
before
before
interacting with
interacting
the cavity,
with the cavity,
and cavity
and cavity
still modifies.
still modifies the emission.
There's a person.
There's a partial effect.
So,
So,
how can we
how
define
can we define
the Purcell
the
effect?
Purcell effect?
So, Purcell
So, Purcell effect is
enhancement
enhancement
of system
of systems
spontaneous
spontaneous emission rate
by its environment.
by its environment.
Okay.
Okay.
So, Purcell
So Purcell
discovered
discovered
scientists
the scientist named
Purcell
Purcell
discovered the
discovered the enhancement of
spontaneous
spontaneous
rate of
emission rate
atoms
of
when they are
atoms when they are
incorporated into the
incorporated
atom.
into a resonant cavity.
So,
So,
and how it
and
works?
how it works?
So, first
So
is
first is
density of state.
density of state.
So,
So
DOS.
DOS.
So, this is
So
the
this
key
is
to
the
the
key
Purcell
to the
effect.
Purcell
Key to the
effect. The
Purcell
key to the
effect is the
Purcell effect is the
modification of the
modification of
density
the
of
density of
electromagnetic or
electromagnetic or
acoustic states
acoustic
available
states
for the
available for the
emitted energy
emitted energy
to couple it.
to couple into.
Then,
Then
second is
second
resonant
is
cavity.
resonant
So, when a
cavity. So
quantum
when a
emitter
quantum
such as
emitter such as an
this is
this
first
is
case,
first
second
case, second is
when a quantum
when a quantum emitter such as an atom is
inside
placed
a resonant
inside a resonant cavity, the
cavity,
cavity
strong
creates a
density
strong density of
at
states at
this
the emitter's
characteristic.
characteristics frequency.
The third is
Third is
emission.
enhanced emission.
So,
So
according to
according to Fermi golden rule,
emission rate
emission rate is
directly
directly
proportional to
proportional to
emission rate is
emission rate is directly proportional to the density of states.
therefore
Therefore,
the density
if the density of states will increase within the resonant
will
cavity, it will
significantly speed up the
significantly speed up the
spontaneous emission
spontaneous
rate of
emission
the
rate of the emitter.
so
So,
emission rate is not
emission
an
rate is not an
intrinsic property
intrinsic
of the
property
emitter,
of the emitter,
it
but
is
it
actively
is
determined
actively
by the
determined by the
surrounding environment
surrounding environment.
and the
And the
condition
condition
and this effect
and
is
this
most
effect is most
pronounced when the
pronounced
cavity's
when the
resonant
cavity's resonant
frequency
frequency
closely
will
matches the
closely matches
emitter's
the
emission
emitter's
frequency.
emission frequency.
The Purcell
The Purcell
the main
the main
criteria
criteria is the Purcell
effect of
effect in
the Purcell
the
effect
Purcell effect operates in the
coupling
weak coupling region.
has
There the interaction between the emitter and the
is much
anode
weaker
much
than
weaker than the
systems decay
system's
rate.
decay rate.
Okay, so the
The
condition
condition
of the strong
of the
coupling
strong
is
coupling
when
is when the
G naught, the
G
coupling
naught, the coupling
atom in the
between atom and the cavity is very, very greater than the decay rate and the
loss damping
loss
factor.
damping factor.
So
So
photons
photons
remain in
will
cavity,
remain in cavity,
repeatedly
repeatedly
reabsorbed and
reabsorbed
reemitted
and
by the system.
re-emitted by the system.
So it means
So it means
this
there
continuous
is continuously exchange of energy
currently between
coherently
atom
between the atom and the
that
cavity,
will
and that will lead to
vacuum Rabi
vacuum
oscillation,
Rabi oscillation, just like in
cavity quantum
cavity quantum
mechanics.
electrodynamics.
The next is
The
what
next is what is
coupling constant.
coupling
How,
constant G naught. How can we define it?
so we don't
So we don't
not go
will not
into
go much
details
into
of this.
details
The
of this, and
formula
the formula of
is
G naught is
proportional to
proportional to mu one to
mu1
transition dipole moment
by h
by
cross
h cross
and under root of
and under
omega
root
by
of omega by 2 epsilon naught
where
v, where
this
this
V is the
v
mode
is the
volume.
mode volume.
From this formula,
From this formula, we can
if
say
we
that
will
if
have
we will have,
so if
so
we want to
if we
have
want
the
to
strong
have the
coupling,
strong
then
coupling, then
there must be
there must be the
lesser
lesser
mode.
mode volume.
Small
So
cavity
small
will
cavity
lead
volume
to
will
the
lead
larger
to the larger
constant.
coupling constant.
Similarly, high
Similarly,
factor
high
will
Q
give
factor will give you small k,
and
and
both
both
factors
factors
is
will
the
increase
strong.
the strong coupling.
So I told you
So I
earlier,
told you earlier that the
effect
Purcell effect
operates in the
operates in the weak coupling regime.
so even
So even in weak
the
coupling, the cavity will change the
continuous
spontaneous
emission rate
emission rate.
and
And
where can we
where
use
can
this?
we use this?
So in the
So
quantum
in the quantum technology, it is used to enhance the
improving
emission rate of single photon sources,
improving the
improving the efficiency,
improving the
improving the efficiency for quantum communication and computation.
in case of
In case of lasers, also we use this
phenomena
phenomena
because it can
because it
improve
can
the
improve
efficiency
the
of lasers
efficiency of
by boosting
lasers by
that
boosting the
which
rate
they are
at which they are
generating
generating the
the photons.
photons.
And the Purcell
And the
factor
Purcell
is
factor is
defined by
defined by
lifetime in
lifetime in the cavity upon gamma cavity
free
upon gamma
space
free
that is
space,
3 by
that is
4
3
pi
by
square
4 pi square
lambda by n
lambda by n cube
q by v.
q by v. So these are the two
These two are the main
these two are the
factors.
main factors. So
If we want to
if we
increase
want to increase the
Purcell factor,
Purcell factor,
then
then
quality factor of
quality factor
gravity
of the
must be
cavity must be high
and the mode
and the
volume
mode volume must be less.
n is the
N
refractive
is the
index.
refractive index. Yeah.
So if
So
fp is
if
greater
FP
than
is
1,
greater
that
than 1, that is
getting
we
the
are getting the
hence
enhanced
spontaneous emission
spontaneous
that is
emission,
fast
that is
decay,
fast decay.
and if
And
fp is
if
lesser
FP
than
is
1,
lesser than 1, that is
inhibited
inhibited
spontaneous emission,
spontaneous emission,
and we will get
and
the
we will
slow,
get the slower decay,
which is in
which is in.
if this is
So if this is the case,
in that
then
case
in
we
that
get
case we get the photonic band gaps.
how can we understand
How can we understand
physically
physically this thing?
high q
High Q,
high q
high Q and small volume cavity,
it will
it will increase, it will
dense the
dense the
state
photonic
at rest.
states at resonance.
Atom will find
Atom will find many available states
that can emit.
that can emit quickly, so that
It will
it will
have
the
fastly the spontaneous emission will be
will
faster
be faster.
and
And
in the photonic
in the
band gap
photonic band gap cavity, there are no available states, since
that's why
that's
emission
why
is
emission is suppressed.
so
So
what
what are the
application is
applications of this? In
laser
case of laser design, where we are
high
using high Q cavities plus gain medium, Uh,
In that case,
in that case, stimulated emission will dominate. So first spontaneous emission, then enhanced spontaneous emission, and then after a particular threshold, it will change into
stimulated emission.
stimulated emission.
Cavity Q
Cavity QED
observe the
will
strong
observe the
coupling
strong coupling,
means coherent
means coherent
quantum
atom
oscillation.
photon
That
oscillations, that is
is
in other
quantum
case
physics,
quantum optics,
where we have the
where we have the
control
control over the emission
that we
lifetime,
can
that is we can
accelerate.
accelerate or inhibit.
In case of
In
nano,
case of nanophotonics,
so Purcell
so
engineering
Purcell
for
engineering for LED single photon sources
and quantum
and
devices.
quantum devices.
So why do we
So
want
why do we want to control the photon emission?
so in a
So in a quantum regime, the goal is to
single
emit
photon
single
and
photons
so
on
that
demand so that we can use it for the
the single photon as
single
a
photon
qubit
as a qubit and can
and
store the memory or
use in
use
quantum
in
communication.
quantum communication also.
And we can
And we
control
can
how
control
fast
how
single
fast and what
photons
state
are emitted.
photons are emitted,
So that we
so that we can use
it as
it
qubits,
as
quantum
qubits,
bits
quantum
carried by
bits carried
photons
by
and
photons,
secure
and secure
communication, quantum
communication,
computing,
quantum computing,
quantum
and
net.
quantum networks.
So for
So, for
example,
example, if
consider
we consider a quantum dot, this is a
it's
semiconductor.
emitting at
It's emitting at lambda nano
lambda.
900 nanometer, and
Radiative
the radiative lifetime
in bulk is
in bulk is
1.3 nanometers.
1.3 nanoseconds.
Now,
Now,
suppose we have
suppose
this
we
one.
have this quantum dot.
Now we have one,
Now we have one cavity,
and we are
and we are placing
this quantum
this quantum dot on this cavity,
which has
which has the
so for gallium
so for gallium arsenide microcavity, so n is equals to 3.5
Q,
q,
assuming the
assuming the q is 2000 and mode volume is
10 is to power.
10 is to power minus 19 meter cube.
So now what will be
So now what will be the
factor?
Purcell factor? So
Is equal
Fp is equals to
3 by 4
3
pi
by 4
square.
pi square.
So after
So after putting the values,
get F
we'll get F is
order.
of the order of 26.
Now,
Now,
if we want
if we
to
want
find out the
to find out the cavity,
lifetime inside
lifetime
the
inside
cavity,
the cavity,
toe
so the
cavity
toe
will
cavity will be
denote
denoted
by F.
by Fp.
So
So
initially it has
initially it has
so the
so
lifetime
the
of
lifetime of
the quantum
the
dot
quantum dot
before
before
interacting with the
interacting with the
cavity
cavity was 1.3 nanosecond.
when after
When after
interacting
interacting with the cavity, it has Purcell factor of 26,
and we
and
get
we get the 50 picosecond. So we can
so we saw
so
that
we
the
saw that the lifetime
lifetime
inside the cavity
has
has
decreased
decreased
from
from
nanoseconds to
nanoseconds to
picoseconds as the
picosecond. That is
spontaneous
spontaneous
density of states
density of
has
states
increased
has increased,
and
and
the
the
spontaneous emission
spontaneous
is
emission is
decreased.
enhanced.
So what
So,
we observe
what
on
we observe
resonance
on
like
resonance, lifetime decreases
drastically, that is
drastically, that
faster
is
emission,
faster
and
emission,
off
and
resonance
off
lifetime
resonance,
closer to
lifetime
the
closer to the
bulk value.
bulk value.
So off resonance
Off resonance 1.1
on
nanosecond,
resonance
on resonance
5
0.25
second. So
second.
we can
So we
measure
can
the
measure
lifetime by
the
using the
lifetime by
film
using the
fluorescence
film fluorescence
lifetime
lifetime
spectroscopy.
spectroscopy.
So next,
So
how can
next,
we
how can
observe
we observe
what type of
what type
cavity
of cavities
have?
it have? So
Cavities are often
cavities are often made at DBR,
where we are having
where we are having the
alternating
alternating
high low
high
reflective
low refractive index
and one
N1, N2, N1.
which will give us
which
the
will
high
give us the high
reflectivity
reflectivity
of
and the strong
confinement.
confinement.
And if we
And
will
if we will
keep a quantum
keep a
dot,
quantum dot in the TPR cavity,
then it will give
then
us
it
a
will give
strong
us a
control.
strong control of emission lifetime.
So we can
So
use
we can use this
application towards the
application towards the making of
photon
single
source
photon
that
source,
cost
that is fast emission will enable
nearly determinate.
nearly deterministic single photon generation, and
We can
we
combine
can
the
combine the
plus
photocrystal
quantum
plus
dot,
quantum dot,
which will
which will give us
compact
the compact
photon
single
sources.
photon sources.
But what is
But what is that
that
this
is
required? That
hypertext
is pi
excitation
pulse
that will
excitation
drive
that will drive the
fully to the
population fully to
excited
the
state.
excited state.
That will give us
That
the.
will give us the strong fluorescence.
So now,
So now,
what are the
what are the
experiments?
experimental signatures of the strong coupling?
So if we are
So if
considering
we are
the
considering the Fabry-Paro cavity plus sodium atom,
if we have the
if we have the bare cavity, then it will give us
single
the
transmission,
single
but
transmission
with
peak. But
sodium
with
atom
sodium atoms
at resonant
at resonant
it will cover
frequency,
the
it will give us the
peak.
double peak splitting.
So
So
this is because
this is because of the
strong coupling.
strong coupling we are getting this splitting.
So
So
this of
in case of
plasmonic,
plasmonic,
we are
so if we are
taking gold,
taking the
gold film plus
gold film plus thin dye film
gold
and gold
nanoparticle
nanoparticle,
uh,
so
of small
of a
diameter
small
that
diameter, then we will have
extremely small
extremely
module
small mod volume,
will
and it will give us the
strong field
strong
confinement.
field confinement. And
We can
we
observe
can
the
observe the
strong
strong
anti-cross
anti-crossing behavior.
that will give
That
like
we will give like
we get like
we
this,
get like this,
not like
not
this.
like this.
So
So
what is the
what
reason?
is the visual picture
Like
of this?
in case of
Like
weak
in case
coupling,
of weak coupling, we will have the
effect
Purcell effect,
where we can have
where
the
we can
either
have the
faster
either faster
emission or slower.
emission or
In
slower
case of
emission. In
stronger
case of
coupling,
stronger coupling,
splitting into two
splitting
modes.
into two modes, that is hybrid atom photon states.
So Purcell
So
effect
Purcell effect cavities can dramatically speed up or suppress emission useful for the quantum light sources.
strong coupling,
Strong coupling,
hybrid
new
light
hybrid light matter
states,
states,
and we can
and we
observe
can
as
observe
a
as
spectral
a
splitting.
spectral splitting,
Both
and
designs are
both
set
regimes are central to the
quantum optics and
quantum optics and nanophotonics research.
and
And
the
in
application section,
application section, single
sources
photon sources we can generate from
and
this we can use
the quantum
these for
information
quantum information processing, and it is a fundamental control of
light matter
light
interaction.
matter interaction.
So let's take
So
a 10
let's take a
break.
10-minute break, then we will start with the
How these
how
cavities
these
have
cavities are fabricated. So we will
about
discuss about these things in details.
Okay, so let's start with how these structures or how these patterns are fabricated. So, in the initial days when we in the initial
In
days
the
when
initial days, when we have the
area,
large area structures,
then
then
we were using
we
the
were
photo.
using the photolithography.
How
Then
the,
how the
what is this photolithography?
photolithography?
Made of
It's made
photo,
of photo,
that is
that
photon
is photon
plus
plus
lithography.
lithography.
Means
Means
patterning is done
patterning is done
by
by
bombarding photon.
bombarding photons.
So that's why it is
So that's
named
why
as
it is named
poly.
as photolithography. So
What is the whole
what is the
process?
whole process?
So in that
So in
case,
that case, photolithography, we use the
UV light,
UV light,
which is of
which
the
is of the
405.
405 nanometer wavelength.
In the
In
initial
the
days,
initial days for the photolithography, we need a hard mask.
what the hard
What
mark
the hard mask mean? Hard mask mean,
all,
first of all,
we will
we will,
whatever the part
whatever the pattern we want,
we will
we
imprint
will imprint that pattern
on some
on
glass
some glass
or laser
using laser
or something.
or
Then we
something. Then we will transfer that pattern
onto the
onto the required substrate, that can be gallium arsenide or copper or gold or silicon.
so
So
how can we
how
understand?
can we understand the process? Start. So
Suppose we have
suppose we have the substrate
and
and
on the top of
on the top of substrate
we have the
we
core.
have the copper film.
Okay.
Okay.
Now to
Now
pattern
to
the
pattern the
we
structure,
have to
we have to apply some photoresist.
substrate,
Substrate,
copper.
copper.
So why this
So why this
photoresist?
photoresist?
What is
What
photoresist?
is
This is
photoresist?
a
So this
photo
is a photosensitive organic medium.
will do
It will be,
when
so when
UV photon
UV
that has
photon
the
that
energy
has
of
the
3
energy of
electron
3
volt, it
electron
will
volt,
break
it
the
will break the
molecular
molecular
bonds between
bonds
these
between
organic
these organic materials,
and
and
wherever the light
wherever
is
the light
exposed,
is exposed,
this reason
this reason
becomes
will
solid.
become soluble.
So
So
then
then
on the top
on the
we
top we have some
mask
mask
that is made up
that
of
is made up of chromium mask.
so what is this?
So what is this?
So it has a
So it has a transparent
plus
glass plus
chromium
chromium
blocking reason.
blocking
So
reason. So
what it will do, it
what
will
it will do, it will selectively exposes the
where we
part
want.
where we want to the make structure.
Suppose this is
Suppose this we
figure
have the figure and the light will expose
only into this.
only into this region. So
Then
then
substrate,
substrate,
copper,
copper,
okay.
okay.
So wherever the
So
light
wherever the light is get
goes, this is
exposed,
after
this is
development.
after development.
Since
Since
photoresist is
photoresist is an organic material and
3 electron volt
3
is very
electron volt
high.
is very
So
high.
wherever
So
this sun,
wherever this energy,
this
this
photon will
these photon
expose
will expose on the
photoresist,
photoresist,
the
the
bonds
bonds
in that
in
particular
that particular part
become
will become
loose and it
loose
will
and
be
it will
soluble
be soluble
developer
in the developer,
and
and
will
it
leave
will leave some
patterns
patterns
on the
on
copper.
the copper.
Then
Then
what we will do
what we will do
for
for
generating the pattern,
generating the patterns in the copper?
substrate,
Substrate, copper.
so what is this?
So what is this?
This is a
This is a
copper agent,
copper agent.
and for
And
etching
for etching the copper,
we use the
we use the
FeCl3.
FeCl3.
So
So
wherever we have
wherever we
the
have the
photoresist, which is
photoresist,
acting
which
as
is
a mask,
acting as a mask,
that is the
that is the
protected copper that
protective
will not
copper, that will
react
not
with
react
the
with the
FeCl3, but the
FeCl3, but the
unprotected copper will
unprotected
remove,
copper will
that is
remove,
etched
that
out,
is
and
etched
we
out,
can get
and
the
we can
desired
get the
pattern
desired
on the
patterns
copper.
on the copper.
In this way, we
In this
design
way, we
our
designed our split ring
resonators pattern.
resonators pattern.
And then
And then
the last step
the
is
last step is
we will
we will
remove
remove
and
this
remove this
remove this photoresist by
in the
developing in the acetone. So
desired pattern.
desired pattern will be we
Suppose
suppose
we want to
we
make
want to make
holes in
holes in
silicon nitride.
silicon nitride.
Then
Then
what can be the
what can be
process?
the process?
So
So
we
so
have
we have
silicon
silicon.
on the top
On
of
the
that.
top of that,
We have
we
silicon.
have silicon nitride.
Then we have
Then we have positive photoresist.
light will come
Light will
at
come at certain part.
Then,
Then,
so we can
so
coat
we
the
can coat the
resist by
resist by using the spin coating,
spin coater.
spin coater.
And this is,
And this is PR.
and then
And then
we will dip
we
into
will dip into the acetone. Mm,
desired
desired
holes in.
holes in silicon nitride.
First,
So
the
first the
structure is
structure is
patterned in
patterned
on
in
the
the
resist. Then we
resist.
are
Then we are
transferring
transferring
structure
the
on the
structure
desired
on the
material
desired
by
material by doing
etching or by
etching
doing
or by
lift-off.
doing
That
lift off.
depends
That depends
on
on the
the
structure, like
structure
which structure do
we want to
we
fabricate.
want to fabricate.
Next is,
Next is,
so
so
I talked about
I
the
talked about the
resist.
resist.
Resist, there
In
are two
resist there are two types of resist. One
positive
is
and
positive resist
negative
and
ones.
the other one is negative resist.
So when we are using the
We are using
positive,
the positive.
in case of the
In case of
positive,
the positive
wherever
resist,
the light
wherever
is
the light is
the bones
exposed, the
are
bonds are becoming
bonds
bonds
loses and
loses and in the
it
it
dissolves
dissolves in the
developer.
developers.
And in case
And
of
in case of
negative
negative
resist,
photoresist,
wherever the light is
wherever the light
exposed,
is exposed,
there
there
occurs the cross
occurs the
linkage
cross
of
linkage of
bonds that
bonds
becomes
that becomes
hard, and
hard,
it is
and
hard
it is
to
hard to
insoluble.
insoluble.
So depending
So
upon the
depending upon
structure,
the structure,
the choice
the
depends on
choice
the
depends on
patterning
the patterning
efficiency. So
efficiency. So
if we are using
if
the
we are using
positive
the positive
photoresist,
photoresist,
then it is good for
then it is good
large
for
edge
large
regions.
edged regions.
If we are
And
using
if we are using negative
resist, that is
photoresist, that is it is
useful
useful
when we need
when we need
small
small
features
features
and need
and
protection,
need protection,
and it's
and
faster.
it's faster also.
So
So
thing is, in suppose positive
positive
PR,
PR,
negative PR.
negative PR.
So
So
if the
if
light
the
is
light is
this,
exposed like this,
what will happen?
what
That
will happen? The resultant, it will,
okay.
okay.
In case of
In
negative,
case of negative,
in case of
in case
positive,
of positive resist,
we have seen
we
earlier
have
that
seen earlier that
substrate,
substrate,
and then
and then
positive PR.
positive PR.
So you
So
can see
you
this.
can see the change. You can see you can clearly see the difference that wherever in case of positive resist,
The light is
where the
exposed,
light is exposed,
the bonds
the bonds
solid.
become soluble,
In case of
and in case of negative here, the bonds become hard, and the
difference in the grade,
difference in the grating size also, meaning Then what are the practical issues in the etching? So
There's one
there's
problem that
one problem that is called undercut problem.
obviously
So
if
obviously
I'm
if
dipping
I'm
my
dipping my
structure
structure in some chemical, it will not go
chem,
the straight away.
it will move
It will move
sideways
in
also.
sideways also because
HN can
etching
see
can
sideways
seep
under the
sideways under the
photoresist. That is
photoresist. That is
etching.
unwanted etching. So
Etching is like
etching
this.
is like
This
this.
is called
So
the
this is
undercut.
called the undercut.
What is the
So what is
solution?
the solution to this?
We
So
have to
we have
adjust
to
mass
adjust
dimension
mass
such that
dimension
we
such
can
that we can
pre-compensate for the
pre-compensate for the
expected undercut.
expected undercut.
And at
And at
nanoscale,
nanoscales,
generally
we generally do
the
the
anisotropic dry.
anisotropic dry
What is
etching. So what is
anisotropic dry
anisotropic
etching?
dry etching?
So
So
we have two
we
types
have
of
two
etching.
types of
That
etchings.
is
That is
isotropic etching
isotropic etching
and
and
anisotropic.
anisotropic etching.
So suppose
So suppose
here we want to
here we want to
out.
etch it out.
We have a
We have
structure.
a structure here.
Isotropic etching
Isotropic
means
etching means
the etching is
the
happening
etching is
in
happening
all
in
the
all the direction.
the etching is
The
also
etching is also
in the
in the
anisotropic.
anisotropic.
We have the
We
sharp
have the sharp etching in
direction.
one direction only.
So there is
So
no
there is no side cut.
but this is
But
generally
this is generally not actually
wet etching. So
wet
that's why
etching. So
we use
that's
the
why we
dry
use the
etching.
dry etching.
So how can we
So
this
how can we just
dry
options of
etching?
dry etching?
So dry
So
etching we
dry
can
etching
by
we can do by
plasma
using
etching,
plasma etching,
reactive ion
reactive
etching.
ion etching.
Then there is one
Then there is
DRI.
one DRI, deep reactive ion etching.
Then
And
there is
then
another
there is one other
ICPRI,
ICPRI,
inductively coupled
inductively coupled plasma
reactive ion etching.
reactive ion etching.
Also we can
Also, we can do the argon ion middling. So we
bombard
can
ions
bombard the ions
on the
on
material
the
that
material so
can
that it can
etch
etch
in the desired
in the desired
reason.
reason.
So these are the
So these
methods
are
of
the
dry
methods of
etching.
dry etching, and
We want an
we want anisotropic etching. That is, we want
in a
the etching in a
single direction.
single direction.
Okay.
Okay.
So now
So now,
when we were using
when we
the
were using the
photolithography,
photolithography,
we were
when
using
we
the
were
UV
using the
light
UV light
for
for
patterning.
patterning,
So
so
we could
we
generate
could
only the
generate
large
only
size
the large
structure
size
that is
structure, that is
micrometers or
micrometers or
millimeter scale or
millimeter scale
centimeter
or
scale.
centimeter scale.
No, when we
So
want to
when we
scale
want to
down
scale down
to our
to
structure to
our
the
structure to the
nanoscale,
nanoscale, then
the
the
problems
of
problem starts
problem
coming.
starts
That
coming.
is because of
That
the
is because of diffraction of light.
so
So
if we
if
have a
we
small
have a
feature,
small feature,
then light will
then
diffract,
light will
will
diffract and it will
broaden the path.
broaden the pattern.
So
So, and
capturing
capturing
the
the
highest
higher
spatial
spatial
frequencies is
frequencies
necessary
is
for the
necessary
sharp
for the
edges.
sharp edges.
So optical
So
system
optical system
will limit
will limit,
and
and
when we lose the
it will
high
lose the
orders,
high orders, and
we will get the
we will
blood.
get the blurred
How can
features. So
we
how can we
overcome the
overcome the
diffraction?
diffraction limit?
So we want
So we want the
we can use
we
the
can use
shorter
the shorter wavelength
or use
or
higher
use higher
numerical aperture.
numerical aperture.
So
So
move from
we moved
this
from photolithography to
electron
electron beam lithography,
and
and
get the
to get the
patterns in the
patterns in the
nanometer.
nanometer range.
So
So
also
also
there is one
there
other
is
problem,
one
that
other
is
problem, that
optical
is optical
proximity correction.
proximity
That is
correction. That is
because of
because
diffraction
of
we are not
diffraction
getting the
we are
smooth
getting the
edges, not
smooth edges,
sharp edges.
not
Suppose
sharp
we
edges.
want,
Suppose you want the structure like this.
okay,
Okay.
then
Then
in patterning,
in patterning,
this is my
this
mask.
is my mask. Suppose this is my mask.
After pattern,
After patterning,
it is
it
becoming
is
like this.
becoming like this.
So at the
So
edge,
at the edges, it is
we
smooth.
don't
So
want
we
this.
don't want this.
So what is the
So
solution?
what is the solution to this?
We are
We are
distorting,
distorting. We are
distorting the mask
distorting the mass
previously, so
previously,
after
so that after this
diffraction,
diffraction, wafer image is correct. So that if
at the edge,
at the edge,
I already
I
give
already give
like this, some
like this some
imperfection.
imperfection.
So that
So that
I can get the
I can get the correct
structure.
structure.
So
So
how
how can we do the modify it? Mask edges we can modify it with serifs or extra notches,
or final
or final
pattern,
printed pattern
so
matches
that
the
final
so that final printed
pattern.
pattern matches the intended design.
So
So then is
so
so
then I want to
then I
discuss,
want to discuss, like,
is there
is there
any possible
the
method
possible method for
making the
making the
structures?
structures?
So there are
So there are two processes.
one is
One is etching,
and the other one.
and the other one is lift off.
So we have
So
seen
we
that,
have seen the etching processes for making nanoholes.
but now we
But
want
now we want to make a structure
that
such that
we have a
we have a
substantial,
example,
we have a
we
sub,
have a substrate,
and
and
want to make
want to make
gold resonate,
gold resonators,
just like SRR.
SRR.
Suppose we want to
Suppose we
make
want to
structure,
make
this
this
is your
structure. This is your substrate,
and
and this is gold resonator.
then
Then
what will we do?
what will we
We will
do?
start
We
with
will start with, we have a
substrate,
substrate.
then
Then
we have
we
positive
have
resist,
positive resist,
positive photo,
positive photoresist,
light exposure.
light exposure.
Yeah.
Yeah.
Okay,
Okay.
then
Then
we will
we
deposit.
will deposit the Thai gold.
Okay,
Okay.
then
And then
we will
we will
lift off.
do lift off.
And what is the
And
final
what is the
structure?
final structure?
We will have the
We
gold.
have the gold resonators.
So what did we
So
do?
what did we do this?
We took the
We took the
substrate, the
substrate, we took
positive
the
photoresist,
positive photoresist,
expose
we
the light,
exposed
then
the
it
light, then it
developed
is developed on the
resist, then we
resist, then we want to transfer the structure on my substrate, which we have the only these gold resonators.
so
So
deposited gold
deposited gold and
position.
deposition. There are several methods of deposition.
Deposition method,
Deposition methods are
like we can do,
like we can do sputter,
we can use the
we can use the thermal evaporator,
we can use
we can use the e-beam evaporator,
we can use
we can use
atomic layer
atomic layer
deposition.
deposition, that is
There are
ALD. So
several
there are several methods. We
methods,
can use any,
and it will get
and it will
deposited
get deposited
on the protected
on the
region.
protected region as well as non-protected
So
region.
now when we
So
put
now when we put it in the
acetone, then
acetone, then it
remove
will remove the material
from this
from this, and
the
the undesired material
undesired
undesired
material will be
material will be
dissolved in
dissolved in the
acetone, and
acetone, and we get the desired structure.
so this was
So
the
this was the
process.
process.
Now
Now
we can also
we
use
can
the
also
phase
use the
mask.
phase shift mask. So
Now
standard
we have
mask,
the two
we have the
adjacent
two
slits,
adjacent slits.
refracted beams,
Refracted beams will overlap,
and we will
and
get
we
the
will get the
resolution.
poor resolution.
But in case of
But in case of,
like if
like, if we
intentionally wherever
intentionally,
there is
wherever we are
phase,
getting the phase shift,
we can
we can
introduce
introduce
intentionally a
intentionally a
phase
pi phase
shift
shift
in
in one
one slit,
slit, so that
so there will be
there will be a destructive
over
interference in the
that
overlap region, and we can get the
clearest.
clearer separation.
So we can
So
how can we
how
implement
can we
this? We can
implement this? We
implement
can
that
implement by using
by
the
adding
by
the
adding the extra glass
delta
thickness delta D,
so that
so that
phase
the
difference
phase difference
pi
delta phi is equals to
2 pi by
2 pi by
lambda by n,
lambda by n,
2 pi
and
lambda
2
d
pi
by
lambda
delta
d
by
by
n
delta
equals
by
to
n is
pi.
equals to
So
phi. So
delta d we get
delta d we can
lambda
get
by
the lambda by 2n.
we will
We will
have
we have
problems
some
regarding
problems
this.
regarding this in the assignment.
So this will be
So
the
this will be
required
the
step.
required H depth.
So example
So
is
example is, if
have
we have the
365
365 nanometer
and
wavelength
refractive
and
index is
refractive index is
1.5,
1.5,
then what will be our
then what will be our
H depth?
H
So
depth?
delta D is
So
equal
delta
to
D is equals to
5 by 1.
365 by 1.5.
That will give us
It
the
will give us
120.
the 120 nanometer approximately.
So we can
So we can
achieve
achieve
by
this is
etching
achieved by
quad
etching
by
quad mask for
depositing extra
depositing
material.
extra material.
So then
So
dry
then
etching
dry etching
versus wet
versus
etching. So
wet etching. So in wet etching we used FeCl3 acids
but
like buffered
hydrogen fluoride.
hydrogen fluoride HF solutions.
So
So
and wet
and
etching
wet etching gives you
isotroping
isotropic etching
also the
and also the
undercut
undercuts, which are unlikely.
and the dry
And
etching
dry etching,
will give us
it
the
will give us the
isotropic
anisotropic
vertical side pole,
vertical
high
sidewall,
precision,
high
and for
precision,
that
and
we
for
use
that we use
plasma
the plasma
ions
ions
and reactive
and
ion
reactive ion etching.
and so
And so
industry people use
industry people uses the dry etching for nanoscale phase shift
assembly.
mass and semiconductor fabrication.
So
So
on a big
on
scale,
a big
we can
scale, we
have
can say that the
plus
photolithography plus
clever optics will
clever
give us the
optics will give us the
fabrication
nanoscale fabrication
with the
with
desired
the desired
precision
precision.
and
And
what are the several
what are the several tricks you, that is
OPC,
OPC,
that is
that is
optical proximity
optical
correction,
proximity correction,
that is mask.
that is mask
We can do the
we
mask
can do the mask
distortion,
pre-distortion,
phase shift by
phase
using the
shift by
phase shift
using the
mask,
phase shift
by
mask,
intentionally
by
doing the
intentionally doing the
destructive interference
destructive
for
interference
resolution,
for resolution,
and by using
and by using the
shorter wavelength
shorter wavelength
higher
and
numerical.
higher numerical aperture.
So what are the key
So what are the key
takeaways?
takeaways? So
Atom cavity
atom
interaction
cavity
is
interaction is
fundamentally a resonant
fundamentally a
process.
resonant process.
Line width depends
Line width
on
depends on
narrowing atoms,
narrowing
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 gases, but broader
gases,
in
but
solids
broader
like
in
gallium
solids like
arsenide,
gallium
Rabi
arsenide, Rabi
oscillations that are the
oscillations, that
coherent
are the
oscillation
coherent
of
oscillation
population
of
between
population
ground and
between
excited
ground and
state and the
excited state
resonant
and the
drive.
resonant drive.
And the condition
And the
for that
condition
is
for that is
omega r should
omega r should be greater than the
damping rate,
damping rate.
and we can
And
make
we can make
these oscillations
these oscillation
by
observable by increasing the field strength.
and
And
cavities
cavities
can
can
dramatically
dramatically enhance or suppress
that
atomic emission, that is the Purcell effect.
if the
If
Q
the Q
Quality factor
Quality
will
factor
be
will
high
be
and
high, and
Q and
so
V
Q
mode
and
volume
V
and
mode volume are the critical
parameters.
fact parameters.
High Q and low
High Q
will
and
be
low V will
strong
give us the
atom
strong
cavity.
atom cavity coupling.
Strong coupling will
Strong
be
coupling will be
there
there will be
coherent
coherent
photons
exchange of
and we
photons,
will get
and
the
we will
vacuum
get the
Rabi
vacuum
oscillation.
Rabi oscillation.
So next
So
we
next
can start
we
our
can start our
assignment.
assignment now.
So the first
So the
question is
first
why
question is Rabi oscillation is the exchange of population
densities
densities
in a blank
in a blank
quantum system
quantum system
due to
due to
strong
strong
incident electric.
incident electric field.
So we saw
So
that
we saw
the
that.
options
So
are
the options
level
are
2
1 level, 2
and
level, 3 level, 4 level. So
we have studied
we
that
have studied that
it's the exchange of
it's the exchange of population densities
first
between
ground
first
state and
ground state
excited
and the
state.
excited states.
So
So
we talk about is
we talk about should we talk about the two level system,
and we talk about
and
the
we talk about the transition dipole moment.
new one.
Mu1.
Okay.
Okay.
So we can
So we can
say that the
say that the Rabi oscillation is the exchange of
population density
population densities
and
in a two-level quantum system due to a strong incident
electrical.
electric field.
Next
The
question.
next question is
Observation of
observation of Rabi oscillation is the signature of
non-classical.
non-classical light, monochromatic light, no coupling, weak coupling,
We
strong
just
coupling.
saw
So
that
we just saw that
we can
we
observe
can observe
Rabi oscillation
Rabi oscillation
with a
when
strong.
there's a strong coupling.
It requires the
It requires the coherent exchange rate to
dominator.
dominate the damping.
So
So
assess
this
result.
is results of strong coupling.
Next is
Next is
graduate
a
student
graduate
perform
student performs a
set of
set of
experiments and
experiments
plot the
and
career
plot the
population
carrier population in the
characteristics at
excited state as shown in the figure below.
so we are
So
given
we are given at the
this
x-axis
omega
it
r
is
t
omega r t by 2 pi,
and the y
and
axis.
the y-axis it is probability density.
So we are
So
asked
we are
which
asked
of the
which
following
of the following curves represent
strong coupling.
strong coupling between light and matter.
In the first
In
case,
the first case A,
we there
we,
are the
there are
continuous.
the continuous oscillation.
So first of all,
So
what are the
first of all, what are the conditions?
Rabi
Rabi oscillation.
Rabi
Rabi
frequency
frequency
to
to
dominate
dominate
the depth.
the damping.
That is
That is
gamma I
gamma I
omega r.
omega r.
So the
So if damping will be large,
if
if
gamma is
gamma is large,
so
so
1 by gamma.
1 by gamma I,
What is 1 by
what
gamma
is 1 by gamma I? That is damping time
is shorter
is
than
shorter than
the
the
oscillation period.
oscillation period.
And how can we
And
define
how can we define the oscillation
we know
period? So we know the
the Rabi frequency?
Rabi frequency.
So we can
So we can define
the
the
oscillation
oscillation
period.
period 1 by omega r.
If this is the
If this is the condition, then oscillations are suppressed.
okay,
Okay,
that is over
that is overdamped or weak coupling region.
But in this
So
case,
in this
the
case,
figure
in the figure A,
It show the
It
sustain.
shows the sustained
There is
oscillation. There
no
is no damping.
sustained
Sustained oscillations
and
and
no
no
damping.
damping.
Okay.
Okay.
Whereas
Whereas
B shows
B shows
oscillation,
oscillations,
but after certain
but after certain time, the oscillations vanished because
it has some
it
damp.
has some damping.
So damping
So
is
damping is visible because after certain
when oscillation.
time oscillations are not
In case
visible.
of
In
C,
case of C,
in case of
in case of C,
C is
C
flat,
is flat,
no oscillation,
no oscillations,
which implies
which
that.
implies that there is no strong coupling.
So in this case,
So in this case, we can answer the question that which
strong.
represent the strong coupling between light and
So
matter.
wherever
So wherever
oscillation,
the oscillations are visible,
we can say
we
that
can say that
this
this strong coupling is visible in that
for
particular
the
part. So for the option A
fourth
and
option.
the fourth option B,
In both the
in
cases,
both the cases,
we can see
we can see the
the
oscillation and there has
strong.
strong
There is strong
there is
coupling
strong
in case of
coupling. In
A.
case of A,
There
there
no
is
damping,
no
but
damping,
in case of
but in
B,
case
there
of
is
B, there
damping,
is
but
damping,
oscillations
but the oscillations are visible.
option A
So
and B.
option A and B.
The fourth
The
question is
fourth question is let omega r be the Rabi
frequency in
oscillation
gamma I.
frequency and gamma I be the damping rate. So we have to choose the correct option
Relating gamma I and
relating gamma and omega r for curve A.
so for curve
So for curve A was undamped.
curve A
Curve A was
that is
undamped, that is damping rate
zero
was zero
compared to the Rabi.
compared to the Rabi frequency.
So
So
gamma I by omega R
omega r
is equals to
is
zero.
equals to zero.
So the correct
So
answer.
the correct answer is fourth.
The next
The
question
next question is
let omega R
let omega r be the Rabi oscillation
frequency and gamma I
frequency
the
and gamma I be the damping rate.
choose the correct
Choose the
option
correct
relating
option
gamma I
relating gamma and omega I for curve B.
curve
So for curve B,
we show
we show
like
like
damped
damped
but still
but still
clear oscillation.
clear oscillations.
In the
In the
undamped,
undamped region,
so damping
so
is
damping is non-zero,
that is gamma I,
that is gamma I is non-zero,
but
but
smaller than the
smaller than the Rabi frequency.
omega R. So the
Omega r. So
condition
the
is
condition is
0
0
gamma I
gamma I
by
by omega r is
is
less
not
than 1.
equal
Is not
to 0,
equivalent to 0,
not
not
equal to 1,
equal to 1.
so
So it's lesser than,
between
it's
the range of
between the range of 0 and 1.
the sixth question
The
is
sixth question is in curve C, we do not observe any
oscillation
oscillation in the probability of finding
carriers in the
carriers in the excited state.
because
This is because
so
so
this is the case
this is the case when
damping time
damping time,
that is
that is
1 by gamma
1 by gamma I,
is shorter
is
than
shorter than the
oscillation
oscillation period.
that is
That is
1 by omega.
1 by omega
This
r,
oscillation,
because oscillation had suppressed.
there is no
There is
time
no
in
time in which
the damping
the
factor.
damping factor is,
The decay rate
the
is so
decay rate is so high,
too high to
too high to
oscillate.
observe the oscillations.
That is
That is
1 by
1 by
gamma I
gamma i
is lesser than
is
1.
lesser than 1 by omega r.
That is gamma
That is gamma I
is greater than.
is greater than omega r.
So the
So this is the correct answer. Or we can write it
gamma I.
gamma I by omega r is greater than 1.
So
So it implies
heavy damping
heavy damping
system is
system is
overdamped,
overdamped,
and we are not
and we are not able to observe the
oscillations.
oscillations.
Next is
Next
consider
is
the
consider a resonant cavity
volume
of volume V and a quality
at a
factor Q at a
particular
particular wavelength lambda
wavelength has a Purcell
has a
factor
Purcell factor
F. The
F.
volume of
The
the
volume of
cavity
the cavity
has been
has been double, and quality factor is also
double at the same.
double at the same
What is the
wavelengths.
new
What is
Purcell
the new Purcell factor of
cavity?
the
So
cavity? So
we know the
we
formula
know the
Purcell
formula of
factor.
Purcell factor is given by,
So
so
that
we saw that
quality factor
quality factor and the mode volume were the key two parameters to
3 by 4
3 by 4 pi square
lambda by
lambda by n cube
into Q by.
into q by v.
Now
Now
we saw
we saw
P is directly
p is directly proportional to q by v.
P dash is
P dash is proportional to q dash by v dash.
Q dash is
Q
2
dash is 2q
and V dash.
and v dash is 2v.
So
So
dash.
p dash,
So basically
so basically
P nu
p
is
nu
equal
is
to
equals to,
so F
so
older
f older f new
from
is equals to f old. There is no change.
so the Purcell
So the
factor same
same
when the
when the
quality vector
quality
and
vector
volume
and volume
triple at
has triple at the same time.
the correct answer
The
is
correct answer is option 3.
question 8 is
Question 8 is, in an optical lithography system, the resolution can be
improved by
improved by
using a lower
using a lower wavelength of light,
and a higher
using a higher numerical aperture of the focusing optics,
using a higher
using a higher wavelength of light, using a smaller numerical aperture of the focusing optics,
or
or
using
using
different substrate.
different substrate other than silicon.
So we talked
So we talked about,
if we
so
want
if you want to
to get a high
get the high resolution,
we have
we
to use a
have to
short
use the shorter lambda,
that is shorter
that is
wavelength,
shorter wavelength, and
high
high
numerical aperture.
numerical aperture.
By changing the
By
difference,
changing the different substrate, there is no meaning.
or also we
Or
can
also we can,
so resolution
so resolution is r
is given
is given by the
Rayleigh criteria.
Rayleigh criteria.
So we can
So we can
decrease the
decrease the lambda
and increase the
and increase the r. In both the cases,
we can use
we can use,
can
we can
Increase the
increase the resolution. So the option
using high number.
using high numerical precision A and B.
The next
The
question
next question is which of the following statement is true in terms of nanofabrication?
so the
So
lithography
the lithography system is used to pattern structures on a substrate wafer. Ellipsometry is used to pattern the structure on a substrate wafer.
lithography
Lithography system is used to measure the thickness of a film. Ellipsometry is used to measure the thickness and optical constants of a film.
okay, so in the
Okay, so in the nanofabrication, lithography system is used to pattern structures on a substrate. This was options to
ellipsometry
ellipsometry. So ellipsometry
is used to
is
measure
used to measure the
an
thickness
optical
and optical
of the film.
constant of the film because it uses the phenomena.
Here we have the
Here we have the
sample,
sample,
the light will
the light will incident,
it will get
it
collected
will get collected
depending on
depending on
S and P
S and P polarization.
collects the
It
data
collects the data
can measure
and we can measure the
thickness and optical.
thickness and optical constants of the film. So the option A and option D.
The next
The
is
next is
fabric
the Fabry-Paro resonance gravity is generally made of two mirrors with reflectivity R1 equals to R2 equals to R.
the figure
The
below
figure below the
the depicts the
video depicts the transmission spectrum of three Fabry-Paro cavities A, B, and C, whose mirror cavities
reflectivities
reflectivity is given by RA, RB, RC,
respectively.
respectively.
So the question
So
is
the question is what can be deduced about the reflectivities of the cavities A, B, and C from the transmission spectrum?
hint
Hint,
consider the relation.
consider the relation between the reflectivity and Q factor.
So we saw
So
that
we saw that
as the
as the
as the reflect
as the reflectivity increases,
resonance
resonance becomes narrower.
that it will
That it will give you a higher
finish.
finish.
What is
What
finish?
is finish? It's an important term when we talk about the cavity.
Finish is
Finish is
how sharp
how sharp the resonance is.
so
So
in the given
in the given figure,
we can say
we can say that
the green
the
curve
green curve has
the green
the
curve
green curve has the higher FWHM
and the red
and
curve.
the red curve has the lowest FWHM.
So
So
higher R
higher R is equals to
higher Q.
higher Q factor.
It means
It means
so
so
RC has the
RC has the highest Q factor.
so the order
So
of
the order of reflectivity is
RA
RA
is lesser than
is lesser than RB is lesser than RC.
the
So
option
the option
4 is correct.
4 is correct.
The next question
The next
is the
question is
following
which of the following cavities will
longer.
have a longer lifetime?
So we
So
know that
we know that lifetime
of a
of
cavity
a cavity
proportion
is proportional to the Q factor of the cavity.
and Q factor
And Q factor
increases
increases with
mirror reflect.
mirror reflectivity.
So we just
So we just
that
found out that
the cavity
the
C
cavity C has the highest reflectivity.
that's why
That's why
the
the
C cavity
C cavity has the
maximum life.
maximum lifetime.
Then the
Then the
12th
12th question is the phase shift mask technique used in nanofabrication
changes the phase
changes the phase of light
in the
in the adjacent patterns,
to the
leading to the destructive interference. A
graduates
graduate student
wants
wants
to use a
to
glass
use a glass n equals to 1.5
PSM to obtain
PSM to obtain a phase shift of 180-degree
for a wavelength
for a wavelength of
of
lambda 600 nanometer.
the thickness
The
of the
thickness of the mask required to obtain
required.
the required phase shift is.
So we
So
just
we
saw
just saw that phase difference
is given
is given by
2 pi by lambda.
2 pi by lambda into nt.
So
So
phase shift of
the phase shift of 180, that is del phi is equals to pi.
so pi is
So pi cancel.
and what are we
And
asked
what are we asked? The thickness. The t is equals to lambda
by 2n
by 2n.
and is the
And is the
reflected.
refractive index.
Here we have
Here we have 1.5 for glass.
so t is
So
equals to
t is equals to lambda is 600
by
by
1.
2 into 1.5.
That is 3.
That is 300 nanometer.
So
So
student have
student have to use
the thickness
the
of
thickness of
we have to use
we have to use the
in the nanometer
300 nanometer thick mask to obtain the
phase shift of
phase shift of 180-degree with a
refractive index.
refractive index of 1.5.
The last
The
question
last question is
is
consider two statements.
first statement is
First statement is a strong coupling between atoms and cavities observed in plasmonic nanocavities.
the second
The
statement.
second statement is plasmonic nanocavities have extremely small mode volume with moderate Q factors.
So
So,
in
in
each of the following
which of the
statements,
following statements are correct?
so for that
We saw that in plasmonic nanocavities,
there will be a
there will
strong
be a strong coupling.
the
And
strong
why the strong coupling
between atom and
between atom and cavity?
cavities.
Because
Plasmonic
plasmonic
cavities for
cavities,
plasmonic
for
we
plasmonic
can
cavities, we
have
can have
extremely small
extremely
model
small mode volume.
and we saw
And
that
we saw that for
condition
condition
for strong
for
coupling
strong coupling,
like
like
we have to
we
have
have to have
small
small
volume
mode volume
and
and
high Q factor.
high Q factor.
These two
These
conditions
two conditions
we can
we
fulfill
can fulfill in case of
plasmonic.
plasmonic nanocavities.
Both the
So
state
both the statement S1 and S2 are true,
and S2
and
is
S2
the
is
correct
the
explanation
correct
of
explanation
S1.
of
So the
S1. So
option
the
is
option A
correct.
is correct.
So this
So
is this was all
this was all
about today.
about today.
So we
So
discussed
we discussed the
atom cavity
atom cavity
interaction, strong
interaction,
coupling,
strong
weak
coupling,
coupling,
weak coupling,
and
and
Purcell effect,
Purcell effect,
Rabi oscillation,
Rabi oscillations,
and how
and how are we fabricating the
structures. So there are
structures. So there are
techniques
different
for
techniques for
fabrication.
fabricating.
So by we
So
can
by we
fabricate
can
the
fabricate the
structures by
structures
using
by using
photolithography,
photolithography,
electron beam
electron
lithography,
beam lithography,
also by
also by bombarding the ions,
focused
that is
beam,
focused ion beam milling.
then
Then
uh, laser
this
writing.
laser writing.
There are several
There are several methods
for
for
patterning.
patterning,
After
and
patterning,
after
we
patterning, we
develop
develop
the
the
structure. After
structures. After
developing,
developing,
we can do
we
two
can do two
processes, lift off
processes:
and
lift
etching,
off and etching.
depending upon
Depending upon the dimension of structures,
we can
we
choose
can choose
which process
which process
for which
for
process
which process we want to move,
that is
that is
etching or lift
etching or
off,
lift
and
off,
in
and
case of
in
etching
case
or
of etching
dry
also dry etching
etching
or wet
depending
etching
on
depending
feature
upon the
size,
feature size,
and such that
and
we got
such that
the
we got the
structures.
structures.
And this
And
was all
this
about the
was all about the nanophotonics. In the next
we will talk
lecture we
about
will talk about the quantum
photonics.
photonics.
So thank
So
you so
thank you
much.
so much.